All right. Well, thank you everybody for joining us today. This is the first ME seminar. I'm not Dr. Landy, but he's, I believe, normally introducing. I know. Hopefully one day, but but Terrence is going to present to us today, so we'll go ahead and let him start. So thank you for coming.
Well, thank you. Yeah, I was hoping I'd be here for my own presentation. But yes, thank you all for coming. I am genuinely impressed this many people showed up. I thought it'd be Chris and a couple of others, but more the merrier. So yes, my name is Terry, and I am presenting today on my master's research that I did over the summer on the microstructure and mechanical properties of GR Cop 42 and HR1. Like I said, this was over the course of the summer, so the majority of this is done at this point, but there is still ongoing research that needs to be finished as the main thing. So starting off, a couple of scientific contributions. So I don't think anyone would doubt me saying that we're in the midst of a new space race, where instead of it being like during the Cold War, instead of it being between the East and the West and separate ideologies and, you know, old rivalries kind of a thing, the new space race is between warring corporations, essentially, and everyone with a 3D printer seems to be popping up trying to be their first person into space, making new rockets, new designs and everything, which has its own drawbacks and its own pros and cons, but one of the best things about it is it has created a revitalized interest in aerospace and space travel as a whole, which again, I don't think anyone would doubt that. One of the things with having this new but slightly different type of space race is because it's on a corporation level, there's now more than ever a focus on cost, what can get us up in space the cheapest, what can get us up there the most efficiently, rather than it just being about, you know, let's throw things at the wall, see what sticks just for scientific contribution's sake. So one of those things that is the hardest to make as efficient, as lightweight as possible, and especially as reusable as possible, is your rocket engine, the very thing that pushes you up into space. And part of that is due to its complexity, and the other part of that is due to the immense pressures and temperatures and differences and vibrations that these things undergo. So you have to make these extremely well engineered. And one of the ideas with that is, well, what if we can 3D print a rocket nozzle? Instead of having it manufactured at separate steps out of full parts, let's manufacture it all as one uniform piece. And the main reason for that is because the majority of large rocket engines use what's known as regenerative cooling. And during regenerative cooling, you have cooled fuel comes down and it wraps around a very complicated system of pipes that go around the nozzle body, basically taking away any of that excess heat during the combustion process and keeping that nozzle wall the correct temperature. And then after that, it goes into the combustion chamber where it has a little bit of a efficiency boost, simply because you have energy put into the fuel. So during the combustion process, you can get more out of it. It keeps things more synced, more aligned, just like cooling your car engine with coolant, but now it's on a much greater level. So this is traditionally done by having a inside rocket nozzle wall, and then after that you have your complicated pipes are wrapped around this entire system. You have those brazed together to make one solid chunk, and then you sandwich that with an outer body. And that is a very time-consuming process. It takes a lot of effort. It's very hard to automate. And on top of that, you have a lot of inefficiencies for your heat transfer, a lot of inefficiencies just because you have so much material there to hold it all together that, again, going back to that idea of additively manufacturing it, what if we can create these cooling channels in the very rocket itself, or the very rocket engine itself? And through traditional manufacturing means, this is almost impossible. It would take far too long to precisely drill everything you need. So instead, let's print it from the ground up with this system in place. Well, if we're going to be 3D printing this, we need to figure out what material we're going to start with. And the material in question to begin with is copper alloy known as GRCOP42. Originally developed at the Glenn Research Center, the 42 part of it stands for the secondary phase that you have in it, which is 4% chromium, 2% niobium, and the rest being copper. And essentially that chromium niobium phase acts as a secondary strengthening phase, so you get better properties just from having that little bit extra in there. And this here is an example of a 3D printed rocket nozzle that is quite a bit smaller. And the reason for that is, although GRCOP42 has tremendous strength and it has very good strength over a wide range of temperature range, still relatively speaking, when we're talking about a rocket engine, those strengths are far too small. So we have a material that is very thermally conductive, but not very strong, again, relatively speaking, for a rocket motor. So we want to scale that up. Well, coincidentally, we also have another material known as NASA HR1, or just HR1. And HR1, the closest material to it that you and I would mostly, or at least I knew, was Inconel 625, where it's fairly similar to that with a whole bunch of added stuff into it. And HR1 has the benefit of being a iron nickel chromium based superalloy. And this stuff is tremendously strong. You can create it through additive manufacturing. Again, it's normally used in a powder form. It has significant resistances to hydrogen, environment embrittlement, oxidation, corrosion, which when you're talking about a combustion process generating thousands of degrees in temperature using gaseous hydrogen, for most rocket engines, it just corrodes them instantly. If you were to use something like stainless steel or even Inconel 625 or titanium, it just melts them and corrodes them instantly. So the benefit of this comes from the HR1 gamma matrix and gamma prime matrix. However, there is one downside of what's known as an eta matrix, which is a nickel titanium phase, but we'll touch on that in a little bit. But essentially, again, we have a material that is tremendously strong, good for additive manufacturing. However, one of the largest downsides is it's not very thermally conductive. Well, what if we could create a bimetallic layer, this rocket nozzle, where on one side we have pure HR1, our strengthening material, and then on the other side we have pure GRCOP42 in order to conduct some of that heat away from our combustion process. The only problem with that, though, is that we're trying to alloy or create something with two very dissimilar materials, which, again, through traditional manufacturing processes, just doesn't work. And especially when you're talking about different 3D printing processes, like typically for HR1, it uses direct energy deposit, which for most of these, the concept is you have a tiny powder particle, you lay it where you want it to be, and then you melt it into the surrounding other particles, which for HR1 definitely works. However, for GRCOP42, that does not work, mainly because it conducts that heat away from it so quickly that you never get a proper bond to the surrounding materials. So we want to combine similar materials. We have an issue with our copper alloy and our iron nickel alloy. Some of it also go through the gas heater, which again, we're just adding energy into the system that we're going to later use. Then they mix together in the powder mixing chamber. And then in the entrance zone of our supersonic nozzle, you have immense temperature and immense pressure. And then as it goes through there, you go through that gas dynamic process, where at the very end, you have your gas is going at supersonic velocities. And as it goes through there, it also carries those teeny tiny powder particles through. And this has the benefit of, again, we can bond almost any dissimilar materials. There are limits, of course, but you can very easily bond dissimilar materials, even to different substrates or surfaces that you wouldn't even think about normally, because none of these particles go through any kind of a melting process. We don't have to worry about any kind of crystal matrix changes. We don't have to worry about any kind of oxidation or corrosion, because it's completely kinetic, where none of it is melted. And all of these particles are held together by plastically deforming as they interact with the substrate or whatever you're targeting. As well, they plastically deform together, and they're basically locked together like puzzle pieces, or like those that old toy with like the monkeys where you try to pull them out of the barrel and they'd all be hooked on together. The exact same thing is happening here. And this is an excellent animation found just to kind of show at a very, very small level what's going on and what we can expect. So going into our research, we have our method, we know kind of our end goal. How are we going to go about this? Well, starting from the very ground up, we begin looking with the powder particles to basically see what are they like at that scale? Are they what we expect them to be? What's the chemistry like? What are some of their properties? And then see how that changes throughout the manufacturing process. And from there, we want to investigate how that changes as we cold spray these into an actual solid or a deposit. And then from there, we want to see how a lot of those properties change throughout a heat treatment process. And for the actual analysis, again, follows almost exactly like what I was saying. The majority of this is looking at your microstructure, a lot of your metallic properties. And then as we work down, we get into more of the mechanical properties of our samples, just to get a good idea of what's going on. So to start off with, all of these samples were manufactured by VRC, where they're all used, or where they were all produced using a VRC Generation 3 high-pressure cold spray machine. And so they were all sprayed onto aluminum blocks, then water jet off and sort of machined, and then we're left with this solid deposit, the solid structure like that. And then from there were water jet cut out into these tensile testing shapes, which were all about 3.5 centimeters long. As for a lot of this, there were different properties for using nitrogen and helium, but that's nothing to worry about too much right now. This is a little table just to kind of keep things straight. The majority of them were manufactured using nitrogen, and then a handful of them were created using helium. And that's mainly because helium is so much more expensive, so we're kind of limited with, we would like to make them all out of helium, but it's quite a lot more expensive. So, which I'll get into in a little bit. So again, starting at the ground level, we want to first see what we're looking at, if it's even in the size that we want. So doing some particle size analysis. For cold spray, traditionally, you want those particle diameters to be between about 10 and 50 microns wide. As you can see here, our distribution, the majority of it falls kind of in that range. There is studies that have shown that for cold spray processes, that having smaller particles kind of trending towards that 10 micron range is better, but again, you have an increase in manufacturing costs to reliably make sure that all your powder particles are that small. So again, all this is it shows that we're in the ideal range for cold spray. So then moving over to some of the characterization, beginning with Jirkov 42, taking it to do some X-ray diffraction. Started here, and we can see that the majority of it is just pure copper, right exactly where we expect it to be. We can see our secondary phase, which is that chromium and niobium mixture, chromium and niobium alloy, which is, again, right exactly where we expect it to be. And then we did also find something that I wasn't expecting, at least, which is the second, or I guess third phase here, which was a different ratio of that chromium niobium mixture, but that's such a small amount, we're not too worried about that. So again, we have that secondary phase, which shows that this is going to be good for creating solid intermetallic bonds. And moving on to same exact thing, but using our HR1 powder. From here, we didn't detect any secondary phases whatsoever. And I didn't include a table of all the elements in HR1, mainly because there's, I believe, like a dozen or so different elements in just teeny tiny quantities. And it blows me away going through this research how homogeneous HR1 is, and there's no distinction between any of it, or there's no differences between any of it. So again, this is basically just showing that our chromium, iron, and nickel are all in the exact amounts that we think, or that we expect them to be. And the same thing can be said taking these over to get lids performed on them, where they all fall exactly in the range that we would expect them to be. Again, just vetting our X-ray diffraction, our XRF, and different methods to make sure this powder is chemically what we want it to be. And there isn't too much of note here, but what is interesting is we have a fairly significant iron peak on both, which could be due to some sort of contamination. That's something we need to look into in the future. But then there is also a pretty significant helium peak, which that shouldn't be there, because as most anyone knows, helium isn't typically just held around in things in nature. It always wants to go away, basically. So again, that's something to look into for the future, but for the time being, the powder is what we think it is, or what we expect it to be. So moving on to some electron microscopy. Here we can see our HR1 powder. Again, all the powder particles are roughly spherical in shape, but they're all about the size we expect. We can see on the zoomed in photo here, we're getting the beginnings of a pretty good dendritic structure. And looking at that with any other forms, or with EDS, again, these all came out quite homogeneous. There's a pretty good microstructure going on there. And the opposite can be said for GR-POP42, which this is less homogeneous. This is the cross-section of a single powder particle, and we can see all these little dots are the green areas here, and that is our secondary phase, our intermetallic phase, that chromium-niobium alloy in there. And that leads to it being a dispersion strengthened material, meaning that this will not benefit as much as HR1 for having a heat treatment process. But again, these phases are very small. That's kind of one of the things that I want to get put here just for a little bit in the future. They're very small to begin with at 75 to 700 nanometers, but they're pretty evenly dispersed. So then going on to looking at actual cold spray solids, this is a couple of interesting, very close-up views of nitrogen and helium sprayed HR1, where you can see a pretty distinct difference in the plastic deformation for our helium sprayed, where we see things are much more stretched out and elongated versus the nitrogen sprayed. And so that shows that for our helium carrier gas, we're getting very good deposition, and it's also creating a better metallic structure, which also shows up when we get into mechanical properties. And same thing can be seen here on an optical microscope level, where on the left we have our nitrogen sprayed, and you can pretty clearly make out just about everywhere any kind of a boundary in between the different particles, and also has significantly higher porosity, versus for the helium sprayed, this is much more compacted together because they're able to fly at such a high velocity thanks to that boost from the helium gas. And again, our porosity here is significantly lower. So all that shows us is that is it's interesting reasoning for in a little bit for the changes in mechanical properties. And this exact same thing can be seen with our copper alloy, not as quite to the same extent, just because our copper alloy, of course, being copper, is a little bit softer, so it deforms quite a lot better. But again, we see a lot less boundary layers, or a lot less boundary lines between those individual particles. So again, that's just showing that the helium sprayed ones definitely are going to have a lot better properties. However, that does still come at the cost of using helium, which is about 10 times more expensive to use than nitrogen. So then taking our solids through the heat treatment process, For the beginning of it, we kept some aside to act as our control group in the as deposited state. Then we started with an hour and a half at 982 Celsius for stress relieving. Then after that, it's furnace cooled, meaning we just turn off the furnace and let it cool for as long as it needs to come to ambient temperature. Afterwards, it's boosted back up to close to the same temperature, but for just a little bit longer in order to solution treatment. And then while those samples were still red hot, orange hot, white hot, they were pulled from the furnace and then immediately sprayed with argon gas in order to quench them as fast as possible. And then after that, they're thrown back into the furnace for another 16 hours at a lower temperature, and then furnace cooled again to a slightly lower temperature for another 16 hours, forcing me to come in at 3 in the morning several times to make sure the furnace actually changed temperatures. That was fun. So either way, at each one of these steps, we have samples being taken out so we can see how things change throughout the heat treatment process. So then starting with some of the mechanical properties, going into the micro hardness testing, in each one of the states from left to right. From left to right, we have a pure copper alloy moving over to our HR1. And then in between, we have different ratios of them, 75, 25, 50, 50, such. And we can see pretty clearly at the start in our as deposited state, we have an increasing micro hardness with that increasing HR1, which makes sense. It's a significantly stronger material. It's not as soft as copper, so that fits with exactly what we imagine it to be. And then as we go into the stress relief process, we see overall a lot of that is lowered by a pretty significant amount, mainly because after that stress relief, we're giving those particles essentially a chance to kind of like relax. They're able to reform their microstructure. And so that internal stress that's led from, or that is brought from that plastic deformation caused by cold spray, it allows that internal stress to be lessened a little bit. So we have better bonding, less internal stress, thus lowering our hardness. And the same thing happens when we go in for solutionizing and quenching. All that is again brought down, but what's interesting here is that if you match up the higher copper content deposits, these actually don't change all that much, but as you start increasing the HR1 content, those come down quite a lot, mainly because HR1, because it's not like GRCOP 42, it's not dispersion strengthened, so it's more susceptible to heat treatment. And then after the aging process, we see kind of that ramp back up of some of them going back to similar hardness levels as before, but again, this is just one of many properties. So then after the micro hardness testing, going into tensile testing, these graphs are laid out the same, where we go from left to right through the heat treatment process, and then also left to right in each step, we have our higher copper content to our higher HR1 content, and then mixtures in between. And in the ultimate tensile test, or the ultimate tensile strength graph here, these peaks that you see, and especially this one carrying throughout, those are the helium spray ones, which, as I said before, we can kind of visualize now that benefit of using helium sprayed rather than nitrogen sprayed, because all of those particles being more bonded together, more squished together thanks to that extra velocity, they're able to retain much better physical properties. And so especially with the HR1 solid, that was tremendously strong stuff. And so in the as deposited case, a lot of this was fairly low with, again, helium being higher, going into the stress relieved stage of it, it was all raised by quite a lot. And then after the heat treatment is where, or after going through the full heat treatment, meaning the solutionizing and the aging steps, that's where we get into some of the biggest differences that still need to be investigated on why, for instance, our helium copper alloy, our helium spray copper alloy actually grows lower than nitrogen, which is the opposite of what we think. And the same thing happens for our HR1 content. It actually starts to go down a little bit. after the full heat treatment process. So those are things to investigate in the future. These ultimate tensile strengths actually fall in line pretty closely to the just the pure extruded material tensile test done. So they're right in line with what we would expect, and they are higher than using other similar methods like direct energy deposit or other thermal methods instead of cold spray. So the only problem with that, though, is although we do have higher tensile strength, that comes at the trade-off of having lower elongation, where we can see in the as positive case, there's almost no elongation whatsoever. These solids are so brittle. I mean, I broke several of them just trying to write on them with a Sharpie to label them. So they're no elongation whatsoever. But as we go through the heat treatment process, especially with the copper alloys, we can see that elongation develops much better. We get much better percent elongation from the tensile tests. However, as I said before, that percent elongation for all the samples is definitely lower than what we would want, especially when compared to like direct energy deposit. Again, I keep going back to that for an example of a thermal additive manufacturing method. So higher strength, a little bit less ductility in our samples, but that's the trade-off going on there. From there, we can also see, as we go through the heat treatment process, our microstructural changes. We're here, this is our HR1 helium sprayed. This is the same picture as before, where we can see things are pretty plastically deformed and stretched out. And as we go into the first heat treatment step, we see those particles are able to reform. Again, they're able to relax. They're able to recreate the expected crystal structure. And then we also see the beginnings of some interesting, very long, very needle-like crystal structure forming. And if you remember me saying at the beginning about HR1, it has another crystal structure that we don't want to see, which is the eta phase. And that is a nickel titanium rich phase. And that essentially acts like a stress concentrator, and it's especially susceptible to helium environment embrittlement. So we don't want to see that. And so seeing that much of it on that scale is not a good thing. However, going into our solutionized step, we see a lot of that is pretty significantly reduced, almost gone altogether. But then after going into the full heat treatment, we see a lot of that reforming. However, now, instead of it being kind of randomly across everywhere, it's distinctly along these intercellular boundaries, which is exactly where we don't want to see it, because that's already where the stress is the highest. And then on top of that, we add what is a stress concentrator and what makes the metal more susceptible to oxidation and corrosion. That's not good. And that's something as well for future research. And then we see something similar but different happening with GRCOP42 as it goes through the heat treatment process, where at the very start, we can see, like I said before, all of these secondary phases, these little tiny dots there are very, very small, only, again, range between like 100 and 700 nanometers, so less than a micron in diameter. However, as we go through our heat treatment process, we see these particles begin to grow, and they begin to kind of gravitate together to make bigger, coarser particles. And that's also part of the reason why some of the mechanical testing as we go through the heat treatment process has lower values than we would expect, mainly because these particles are good to have. This secondary phase is good to have. However, when they start lumping together too much, we lose that dispersion strengthening because it's not stopping our material from moving around because they're all clumped together so much. And this is just looking at things with an optical microscope. This is our 50-50 mix, where 50% of it, GRCOP42, 50% HR1, sprayed together. And we can see that the photos actually begin to look like they're darkening as we go through the heat treatment process. And that's not anything having to do with the microscope. Trust me, I had to check. That has to do with those secondary phases becoming more and more abundant. And so in the top here, we can see things are pretty light. We don't see a whole lot of extra stuff, which, just for reference, the Copper color is obviously our copper alloy, and the grayish color is our HR1 alloy. And as we go through here, we can see the start of a lot of distinct interboundary layers, boundary layers in between, and we also see our copper beginning to darken more and more, and that's because those chromium niobium precipitates are growing through the heat treatment process, and so they're looking a lot more apparent. And that's true all the way throughout. So there is definitely a change. This unfortunately was one sample we weren't able to look at with SEM, and that's kind of more future work that we would like to do, because that's of particular interest. Is if we're talking about creating a bimetallic layer with this stuff, or a bimetallic solid with it, we really want to know, well, okay, if we have eta-phase growth, is it happening at the same time at these boundary layers in between our copper alloy and our HR1 alloy, or is it just in the HR1 alloy? So those are things like that we unfortunately ran out of time for. However, that is on the docket for future research. So, doing pretty good on time. In conclusion, wrapping up, we were able to look at the powder particles and get a good characterization of them. We were able to look at some of those properties and sort of how they vary between the two materials. Again, relying on, or falling back to exactly what we expect them to be. And then going through the cold spray process, we were able to look at how those properties from the powder state changes to the solid state. And we were able to see some of the mechanical properties of that as well. And then of course, going through the heat treatment process, seeing how those things change. Again, one of the most significant things of this research was seeing the difference between using the nitrogen gas and the helium gas, mainly because it's obviously it would be better to have it cheaper, produced with nitrogen. However, if we don't have a material that's strong enough, that's also not as good. So as with anything, there's always a balance that has to be achieved. So yeah, then going into future plans for future research. Currently, the largest bit of it is expected to be a balance between basically taking what we already have and kind of just through trial and error, figuring out with the heat treatment process what we can do to decrease some of those problems, like the growing secondary phases. If we can only, or if we only need to take it into the furnace for an hour and then that's it, those are the best properties possible, then you go with that. Or we would also like to do hipping, which is hot isostatic pressing, I believe. I don't remember if it's higher, whatever. Basically, another form of heat treatment where you're compressing the solid in order to get rid of some of that porosity. That's another process we would really like to look into, and that's definitely on the docket for future research. And then the other big thing is using a number of different methods to identify in the HR1 alloy that secondary eta phase, because although we are able to see that secondary phase and we are able to see that it's titanium rich, because those crystals are so thin, even on a microstructure or even on a micro scale, because they're so thin, it makes it almost impossible to identify through the methods that we've already used, like using XRD or SEM or EDS or anything like that. So there are a few ideas for analyzing both the secondary phases for both materials, such as dissolving them in some kind of acid and then taking it also through different processes. And then as well, there's a number of different mechanical testing that we would like to do, like fatigue testing. Thermal conductivity is one of the biggest ones, mainly for copper, because it is supposed to be very thermally conductive. So we want to see how that changes throughout the heat treatment process, because maybe it gets stronger through the heat treatment process, but if it's not thermally conductive, then we just as well not use it at all. Majority of that, of course, there's other ones. Oh yes, and further libs analysis, because that's something I've talked quite a few times with you and Dr. Dvacher about in order to get a better idea with some of that stuff. So I would like to wrap things up by just saying thank you to the NASA representatives and NASA in general, because they're the ones who provided funding for this, and they're the ones who kind of provided the groundwork in order to do any of this. I'd like to thank the RC. They're the ones who actually physically manufacture these parts, and I was able to bug them quite a lot, asking different questions about the manufacturing process, which was very important for doing any of this research. Again, just thanking the mechanical engineering department as well as the MI department. Everyone has been so tremendously helpful. There's been so many times where I have to ask a question from a random person who just happened to walk by, and I mean, every single person in both departments is just very, very pleasant to deal with. The biggest ones, and actually, I should say, who's kind of in charge of this research on campus is Dr. Josty and one of his PhD students, Amanth. They were also a tremendous help where the both of them, if I ever had to, learn a new method in order to actually get this work done, or if I had to use a certain machine or something, both of them at the drop of a hat would be able to help. And then in the mechanical department, James, Todd, Michael, and Satish. Actually, I don't know if Satish. Either way, they were all also, again, able to help a ton. And if it wasn't for James and Todd especially, I wouldn't have been able to do any of the tensile testing because I wasn't going to try and run that machine myself. And so they were tremendous help there, and we stayed multiple days, stayed way longer than I would ask anyone to stay, doing their work, but they stayed there to help me. So again, I had a lot of help with a lot of this. So with that being said, now it's time to open it up to questions. So if anyone has questions, yes.
First of all, excellent talk.
Oh, thank you.
For your future research, every time you said we're going to look at that in the future, is that what you're doing for your PhD? Are you continuing this and investigating this, or is it just done somebody else?
That's a little up in the air right now. It definitely could be turned into my PhD research. This whole topic was actually kind of brought to me very last minute, and it was more of a like, hey, you're the most likely candidate for this. And so my PhD research, I don't expect it to be on this, but it could be. I will be helping Dr. Josty still with a lot of this research, though, especially in the coming year, where I expect, especially we're hoping to do some sort of publication in the coming spring. We still have a few loose ends to kind of tie up, and then moving into the secondary phase of this research, I've been kind of asked to, if I'm not in charge of it for the PhD research, if I can at least help bring whoever is going to take the reins, if I can at least bring them up to speed on everything done so far and kind of be a contact, I guess. So, yes. Yes.
So my question is, how did you come up with the heat treatment recipe, or was it given to you?
That was thankfully given to us from NASA, where there was a few other papers that have been done previously that had the exact same, or a few bits of other research that have been done previously that had the same heat treatment process. But no, that was entirely, they basically wanted to do some sort of heat treatment, and NASA was like, here you go, don't ask too many questions, just do it. Sort of a thing. So yeah, but that is backed up by other papers that have done similar things. And I think that process is mainly, at least from what I could figure out, this would be a good question for more of a metallurgical engineer, but at least from what I could figure out, it's more of a balance in between the HR1 heat treatment process and the GRCOP42 heat treatment process, because they're quite a bit different and they rely on significantly different temperatures, and this is essentially just some sort of a meeting in the middle between the two. Yeah. Yes.
Yeah, very good talk and pretty thorough work as well. So I had a couple of questions. First of all, I'm kind of new to this area. So first thing would be the end goal was to create kind of the chamber with channels embedded in it, right? So that the coolant can, the fuel can go through it to cool it. But I'm not sure if I missed it, but so the samples you tested were like a homogeneous samples, right? So it didn't have a channel embedded in it. So in that case, right, if you have a channel embedded in it with this cool spraying technique, right, will that, what's the chances of having that channels create stress locations, stress concentration locations?
Oh, it would create stress concentration locations. And I mean, this research is essentially the dipping our toes into the water to see what we can expect. All right, let me pull this up. Where, let's see. So these rocket nozzles have been 3D printed using other methods, and the testing done with them has been very promising for in the future. However, again, wanting to do that with some sort of cold spray, this was basically just an initial look at if it would even be a good idea, depending on a lot of the properties that we're seeing. So yeah, having some sort of channel in there would definitely create stress concentration zones, but that would just be something to factor into the design of the rocket nozzle itself.
So yeah, then the other two questions would be then, do you have an idea of it, like the heat treatment, since you said part of it was quenching it? It's the same issue would be like, we have thoughts on like, if it's a giant size conical thing with a bunch of channels in it, you can quench the outer surface. How do you get the inside channels to be quenched as well?
Yeah, that's definitely one of those things we even ran into when we were trying to do the quenching. That's a little complicated, at least with trying to just hold it with a gloved hand and spray at it with a tube coming from a giant argon tank. It is a little bit finicky. I don't know off the top of my head. I would expect that you could do some sort of, taking this entire body and putting it into some sort of a chamber where you'd evacuate all the gas and then fill it with argon as fast as possible. I do know that the argon quenching is not required. Talking with the NASA representative, he did mention that it can also just be standard air cooled, like just pulled out of the oven and just allowed to cool in ambient air. But the quenching with argon, in theory, would be better in order to remove, or in order to keep down some of that possible oxidation and corrosion happening. So that would definitely be, something tricky. I expect that would be a whole study on itself, being able to do something like that.
Yeah, the last question would be, since you're dealing or you're trying to make something that has like extreme temperature, that has vibration, force, right? Do you have thoughts on like how to increase the ductility, because you don't want anything to be brittle, but has so much vibration?
Yeah, that would definitely be, that is definitely a concern, especially when you're talking about a rocket nozzle that, again, going through with that vibration and everything, even just going through, 60 seconds of going through that combustion process is tremendously taxing on this material, or on any rocket nozzle material. And then also for in the future, this wanting to be some sort of a reusable rocket engine, that would definitely be something that would have to be thought about. I don't know off the top of my head any ways with cold spray to reduce or increase that ductility. So yeah, that would definitely be something to look into. And again, that would be something that could also be looked into with wanting to do cyclic loading or doing some kind of fatigue testing. That'd be another pretty significant thing. As well, kind of going also back to the heat treatment and the quenching parts of it. Again, part of the future research is to hopefully narrow down different parts. So instead of going through that entire process, maybe we don't have to do the quenching altogether. Maybe again, we only have to have it go, 1 hour in the furnace, and that might lead to better properties. So there's a lot of things there that could be done even before looking into different, alloying methods or anything like that. So it'd be very interesting. Anyone else? And I can go to other slides if anyone missed anything. The numbers there are kind of small. Yes.
I had two.
Okay.
First one was kind of on the the application of it. You talked how the copper can't use the heat, so you use different application. And with the cold spray, how does that actually get applied? If you apply it onto a substrate, are you going to be able to work those grooves into the rocket engine?
That would just be a matter of basically large-scale printing, where more than likely it would be printed from, the bottom up, like most 3D printing processes, where you would essentially have to design it. I guess there would have to be a lot of work going into aligning those cooling channels to make sure it would be able to print in such a way that you could still have, desired thicknesses, and you're not going to be blowing through walls that are farther down or anything. So that would definitely be something. I do know there are some ideas out there of doing, layer by layer, and then you have some kind of a body in between, like just simple sand or something, and then you would print directly onto that, and then after things are done, you basically just pour out the sand from there. So you would have some sort of a substrate that you would be coating. Again, that would definitely be something to look into for basically just seeing, how possible it would be, because,
Would it be like a full nozzle 3D print where you got a material that you're going to use to fill your void spaces, let's say, but it reacts with some other chemical that you have, or I don't know, you can pick it up and just shake it a whole bunch until everything falls out, depending on that you want to do. But
oh yeah, there's definitely a lot of possibilities, and I will say that is one area I'm a little short on in my knowledge, is I guess more of the intricate knowledge about 3D printing and about, I know it's not as simple as throwing a design into a computer and saying print it. There's a lot more that goes on in there. So there are a lot of different things like that a person could do, and if you have good ideas on that, that's currently on, exactly where NASA's currently looking into, because at least to my knowledge and my finding, there hasn't been any kind of 3D printed rocket body with those cooling channels contained within the rocket nozzle itself. And I do know there are also a number of methods where you can kind of do an in-between of the original method or the current method, which is, having your inner layer, and then you sandwich that with some kind of pipes, and then then you sandwich it with an outside layer. You could do something similar to that, where you instead of spraying from the ground up, you essentially spray in kind of a radial direction around. I've seen some stuff on that. Again, a lot of that would just fall under the guise of, how you want to design your nozzle and how you want to design those cooling channels. Does that answer your question?
yeah. Second one is a little bit more of the metallurgy side of it. During the heat treatment processes, did you find that there was any warping or anything going on that would be an issue if, as you scale this up and heat treat? You finding any issues with that, warping the samples?
I didn't find any apparent warping of any samples. That is sort of one of the benefits of starting this with cold spray, because I do know that is actually a pretty significant problem, especially with HR1, having that produced with other additive manufacturing methods like DED or powder fusion. Is it runs into quite a bit of warpage that can happen. But the heat treatment process was essentially supposed to be low enough that neither of the materials would experience any kind of major deformations like that. Like anything, I suppose it's possible. That's kind of one of the things where a person would have to be scaled up to a size like what's currently being done or bigger, just to see, I guess, what the effects are. That is also another thing that is of quite a bit of research is post-manufacturing, like finishing effects, or not finishing effects, but machining the sides down, getting rid of like all those uneven edges, different things like that. That's another one of pretty significant research, because even if you have your body, but there's still some sort of a little bit of a defect, that can also, in a roundabout way, can kind of act like a stress razor or a stress concentrator. So there are things like that that are definitely of research, but at least on my end, dealing with the samples, I didn't notice any kind of warping, deformations, anything like that.
Cool, thank you.
Of course. Yes.
Have you done any work towards finding any theoretical calculations to express how the properties function in the real world? By that I mean, like, stress equations, if you're looking to
Oh.
any of those with your wishbone samples.
No, I haven't personally. A lot of this work was just getting the tensile testing data to actually look like tensile testing data, because dealing with the brittle properties of these materials made for not too nice of stress strain curves. So there's a lot of that could definitely be done. That is another area that would be more so on my end to do for the phase 2 stuff, is to better interpret the tensile testing data that's already there, and then also apply that to other things, and actually putting that into the real world. That'd be good.
I thought if you're doing this project for NASA for them,
Mhm.
a pound of paper is probably going to be a lot cheaper than a pound of whatever material you're using here.
Yeah,
I don't know
exactly.
your cost analysis there, but just a thought on the future research.
Oh, sure, absolutely, yeah. And I mean, there's a lot of that where I don't know if that would make it into the phase 2 stuff. It probably, I'll definitely keep that in mind. Again, a lot of this is just supposed to be very ground level to even see if further research is feasible or is a good idea, or if this is just a dead end sort of thing. So there are definitely a lot of things like that could definitely go into it. Anyone else? Any other slides you want to see? All right. Pretty good on time, I think. So, awesome. Well, thank you everyone for presentation.